In mathematics, the directional derivative of a multivariate differentiable function along a given vector v at a given point x intuitively represents the instantaneous rate of change of the function, moving through x with a velocity specified by v. It therefore generalizes the notion of a partial derivative, in which the rate of change is taken along one of the coordinate curves, all other coordinates being constant. The directional derivative is a special case of the Ghetto derivative. Definition: the directional derivative of a scalar function along a vector is the function defined by the limit in the context of a function on a Euclidean space. Some texts restrict the vector v to being a unit vector. Without the restriction, this definition is valid in a broad range of contexts, for example where the norm of a vector is undefined. If the function f is differentiable at x, then the directional derivative exists along any vector v, and one has where the on the right denotes the gradient and is the dot product. Intuitively, the directional derivative of f at a point x represents the rate of change of f with respect to time when moving past x at velocity v. Variation using only direction of vector for Euclidean space. Some authors define the directional derivative to be with respect to an arbitrary, non-zero vector v after normalization, thus being independent of its magnitude and depending only on its direction. This definition gives the rate of increase of f per unit of distance moved in the given direction. In this case, one has or in case f is differentiable at x. This definition is not equivalent with the one above except when v is a unit vector. Notation: directional derivatives can be also denoted by where v is a parameterization of a curve to which v is tangent and which determines its magnitude. Properties: many of the familiar properties of the ordinary derivative hold for the directional derivative. These include, for any functions f and g defined in a neighborhood of, and differentiable at, sum rule, constant factor rule, for any constant c, product rule, chain rule. If g is differentiable at p and h is differentiable at g, then, in differential geometry, let M be a differentiable manifold and P a point of M. Suppose that f is a function defined in a neighborhood of P, and differentiable at P. If v is a tangent vector to M at P, then the directional derivative of f along v, denoted variously as, or, can be defined as follows. Let gamma minus 1, 1, M be a differentiable curve with gamma equals P and gamma equals V. Then the directional derivative is defined by this definition can be proven independent of the choice of gamma, provided gamma is selected in the prescribed manner so that gamma equals V. The Lie derivative of a vector field along a vector field is given by the difference of two directional derivatives. In particular, for a scalar field, the Lie derivative reduces to the standard directional derivative. The Riemann tensor directional derivatives are often used in introductory derivations of the Riemann curvature tensor. Consider a curved rectangle with an infinitesimal vector delta along one edge and delta along the other. We translate a covector s along delta then delta, and then subtract the translation along delta, and then delta. Instead of building the directional derivative using partial derivatives, we use the covariant derivative. The translation operator for delta is thus and for delta. The difference between the two paths is then it can be argued that the non-commutativity of the covariant derivatives measures the curvature of the manifold. With R the Riemann tensor of course and the sign depending on the sign convention of the author. In group theory, translations in the Poincare algebra, we can define an infinitesimal translation operator P as for a finite displacement lambda. The unitary Hilbert space representation for translations is by using the above definition of the infinitesimal translation operator. We see that the finite translation operator is an exponentiated directional derivative. This is a translation operator in the sense that it acts on multivariable functions f as rotations. The rotation operator also contains a directional derivative. the rotation operator for an angle theta, i.e., by an amount theta equals theta, about an axis parallel to equals theta. Theta is here L is the vector operator that generates, so it may be shown geometrically that an infinitesimal right-handed rotation changes the position vector x by, so we would expect under infinitesimal rotation. It follows that following the same exponentiation procedure as above, we arrive at the rotation operator in the position basis, which is an exponentiated directional derivative. Normal derivative. A normal derivative is a directional derivative taken in the direction normal to some surface in space, or more generally along a normal vector field orthogonal to some hypersurface. See for example Newman boundary condition. If the normal direction is denoted by, then the directional derivative of a function f is sometimes denoted as. In other notations in the continuum mechanics of solids, several important results in continuum mechanics require the derivatives of vectors with respect to vectors and of tensors with respect to vectors and tensors. The directional directive provides a systematic way of finding these derivatives. The definitions of directional derivatives for various situations are given below. It is assumed that the functions are sufficiently smooth that derivatives can be taken. Derivatives of scalar-valued functions of vectors. Let be a real-valued function of the vector. Then the derivative of with respect to in the direction is defined as for all vectors. Properties. If then, derivatives of vector-valued functions of vectors. Let be a vector-valued function of the vector. Then the derivative of with respect to in the direction is the second-order tensor defined as for all vectors. Properties. If then, derivatives of scalar-valued functions of second-order tensors. Let be a real-valued function of the second-order tensor. Then the derivative of with respect to in the direction is the second-order tensor defined as for all second-order tensors. Properties. If then, derivatives of tensor-valued functions of second-order tensors. Let be a second-order tensor-valued function of the second-order tensor. Then the derivative of with respect to in the direction is the fourth-order tensor defined as for all second-order tensors. Properties. If then,